everyone, welcome back to the channel. So today in this video lecture we're going to be learning about Dijkstra algorithm. So we'll be learning about the single source shortest path problem, what is it and how to solve that using Dijkstra algorithm, the underlying principle of this algorithm as well as its code implementation. We'll also learn how to retrieve the actual shortest path itself, okay, the set of nodes which constitutes that shortest path. We'll also learn a few optimizations in this video lecture, like whenever we find the target node for which I want to find the shortest path from the source vertex, I will stop my algorithm right there without evaluating the shortest path for the rest of the nodes. So we'll discuss these things in detail, while we'll also discuss a lot more optimizations of this algorithm in the next videos. So let's understand the single source shortest path problem. So in this problem we're given a source vertex or a source position, which is this node home. So suppose you are a university student and here this represents your university and this is your home, where between these two locations there is a set of roads connecting these locations A, B, C, D, E, F, which are intermediate locations between the home and the university. So this is university. You want to use some, a set of these roads to reach the university such that the path that you choose is the shortest path. Okay, so let's check out the possible paths to reach the university starting from our home. So one of the path would be just move from home to node number C, then from C to E, then from E to finally the university. That is going to cost 5 plus 2 plus 4, that is 5 plus 2 7 plus 4 is 11. Okay, then another path would be move from home to C, then from C to E, then from E to F, and finally from F to the university. That is going to take 5 plus 2 plus 1 plus 2, that is 7 plus 1 8 plus 2, that is 10. Let's take one more route. Move from home to B, from B to E, then from E to F, and finally from F to U. So that is going to cost me 2 plus 6 plus 1 plus 2, that is 2 plus 6 8 plus 1 9 plus 2 11. Okay, let's take another route. Move from home to B, then from B to D, then from D to F, and finally from F to the university. That is going to give me 2 plus 1 plus 4 plus 6. Okay, 2 plus 1 plus 4 plus 2. Okay, that will give me 3 plus 4 7 plus 2, that is 9. Let's take another path, that is move from home to A, from A to D, then from D to F, then from F to U. That is going to give me 3 plus 3 plus 4 plus 2, that will give me 6 plus 4 10 plus 2 12. Okay, so this is the shortest path that I am getting here, that is move from home to B, then from B to D, then from D to F, and finally from F to the university. Okay, giving me a total path length, total shortest path length of 9 units. So 9 is the answer for this given test case. So we have a home, we have a university, the shortest path that we have is of length 9. Okay, so how we can solve that, how we can arrive at the shortest length of the path given a source vertex. Now this is the shortest path problem, that is we are given some source vertex, we want to find the shortest path till each node of the graph. That is, if I know the shortest path till B, so I am sure that the shortest path length till node number B is S. Then I can always calculate the shortest path till node number E, node number D, because that will be nothing but S plus 6 for this node. If I come through this node B, and for this D it would be S plus 1. That's the idea. So we have shortest path till node number B, then I can evaluate the shortest path till its adjacent nodes as well. That's the idea. Let's see how we can solve that problem. Let's describe the underlying principle of Dijkstra algorithm with an example. So let's take this example. We have 6 nodes numbered from 1 to n, and the source node is node number 1. Okay, this is our source node. I want to find the shortest path till each node of this graph. How would I find that? Now first of all, I will initialize the distance for each node to be infinity. So infinity is basically nothing but a very large number which exceeds the total weight of this graph. So it must be very large, that is exceeding the constraints of the edge weight. Okay, and then since the source vertex is node number 1, the distance, the shortest distance till source vertex would be 0. Why? Because it is the source vertex. We are starting from this vertex. This is the vertex from which I want to find the shortest path till each node of the graph. So how would I represent that? So I would use an array. Let's call it distance array. Okay, so this is the distance array. Since the nodes are numbered from 1 to 6, all of these nodes are initialized with a very large number. Let's call it infinity. Okay, this is infinity. Now this is the source node, that is node number 1, and this is initialized with 0. Okay, now this is our distance array where this node number 1 is initialized with 0. Now what I'm gonna do is, the underlying principle for this algorithm is that if I know the shortest path till node number 1, then I can always calculate the shortest path for its adjacent nodes, for node number 6, 3 and 2. Okay, how? So for that I'm going to use a priority queue. So a priority queue will be initialized. Why priority queue? Because what I'm going to do is, I'm going to push the nodes for which I have calculated the shortest distance into the priority queue. For instance, assume that I have calculated the shortest distance till node number 6, 3 and 2. Then I'm going to push these nodes into the priority queue. So to find the shortest path till any node, I'm going to pick that node out of these 3 nodes which has the least distance. I'll explain how it works. So I will use a priority queue. Okay, so initially I'm going to push this node number 1 with its distance. So the priority queue will sort these pairs according to their distance from the source node. So initially only the source vertex is pushed into the priority queue, that is node number 1. Okay, now I will pop the node from this priority queue which has the smallest distance. That node is this node number 1, because we have, this is the only node that we are having here, that is node number 1. So I pop this node out of the priority queue, that is node number 1. Its distance is 0 because it is the source node itself. So I traverse its adjacent nodes. The adjacent nodes of node number 1 would be node number 6. So what I am saying, I already have the shortest distance till node number 1. The shortest distance till node number 6 would be 0 plus 14, that is 14. 0 plus 14. Now I am going to compare the distance for node number 6 which I already have in the distance array. So we can see that for node number 6 the distance that we already have is infinity. We can see here it is infinity. So 0 plus 14 is better than infinity. So I replace this infinity with 14. So this is replaced with 14. Then since I have updated the result for node number 6, I'm going to push this node into this priority queue. So I'm going to push node number 6 into the priority queue along with its shortest distance, that is 14. Now move to another adjacent node, that is node number 3, okay, this one, and calculate shortest distance till node number 3. So the shortest distance would be 1, so 0 plus 9. 0 plus 9, that is 0 plus 9 is 9. Now 0 plus 9 is better than infinity, so I will update the distance for node number 3 as well. This will be updated with 9. Okay, so I will put node number 3 along with its distance, that is 9. Okay, now traverse the last node, that is this node number 2. Okay, its distance would be 0 plus 7, that is 7. Now 7 is better than infinity, so update the result for node number 2. So update the result for node number 2, put it as 7. So push node number 2 along with its distance to be 7. Okay, now I have these 3 pairs, 3 nodes with their corresponding distances from the source node. Okay, now I have traversed these 3 adjacent nodes of this given node, that is node number 1. Now after these 3 nodes, I'm going to pick the node which has the shortest distance. That node is going to be this node number 2, this one. Its shortest distance from the source node is 7. So I'm going to pick up this node and its distance is 7 from the source node. So I will pick node number 2, so this will be popped out. So it has a distance of 7, so I will traverse its adjacent nodes. So let's traverse this one, that is node number 3. So if I calculate the shortest distance till node number 3 through node number 2, it would be 7 for node number 2 plus 10, that is 17. Now the distance that we already have for node number 3 is 9. Now 17 is not better than 9, so we are not going to update the distance for node number 3. Then I traverse this node, that is node number 4, and the distance will be updated because the distance for node number 4 is infinity, and the shortest distance that I calculate through node number 2 would be 7 plus 15, that is 22. So 22 is better than infinity, so update it to be 22. Okay, now also push this node into the priority queue along with its distance. So put this node into the priority queue along with its distance. So I have traversed all the adjacent nodes of node number 2. Now pick up another node from this priority queue. So pick up the node which has the shortest distance. It would be this node number 3. So pick up node number 3. So pull out this node from priority queue. Now traverse its adjacent node. Node number 6, node number 6. So if I calculate the distance for node number 6 through node number 3, it would be 9 plus 2, that is 11. Now we can see that 11 is better than 14. So I will update the distance for node number 6. So it will be updated to 11. That means it is better to move from 1 to 3 than from 3 to 6 than to move from 1 to 6 directly. Now let's traverse the another vertex, that is this vertex number 4. The distance would be, it would be 11 plus, it would be, for node number 3 we have 9 plus 11, it is 20. 20 is better than 22, so I will update it with 20. So for node number 4, so since I had updated this node number 6, I also have to push it into the priority queue. So I will push the node number 6 into the priority queue along with its node distance, that is 11. Okay, now let's traverse another node, that is this one. node number 4. Its distance would be 20 if I come through node number 3, because for node number 3 the distance is 9. So 9 plus 11 would be 20, which is better than 22. So I will update the distance for node number 4 as well. It would be 20 now. And I'm going to push this pair also into the priority queue. So I will push node number 4 along with its distance, that is 20, the new distance. Fine. Then traverse this node number 2. It is the distance would be 9 plus 10, that is 19. But for node number 2 we already have a better answer, that is 7. So we don't have to push this node. Okay, so we are done with node number 3. We have the shortest distance till node number 3, and it is going to be 9. Now pull out the node which has the shortest distance. That would be this node, that is node number 6. So pull out node number 6 from this priority queue, this one. Now compute the distance for adjacent nodes of this node number 6. That would be this node number 5, and the distance for node number 5 would be, for node number 6 it's 11. For node number 6 it's 11. So 11 plus 9 is going to give me 20. 20 is better than infinity. So update the result for node number 5. Update for node number 5, put 20 and push node number 5 along with its distance, along with its updated distance. Traverse this node, that is node number 3. We can see that for node number 3 the distance would be 14 plus 2, that is 16. But we already have a better answer for node number 3, that is 9. So we don't have to push this one. For node number 1 we already have a better answer, that is 0. We can't get better answer than 0. So we are done with node number 6. Now pull another node with the shortest distance. That would be this node, that is node number 6 again. But for node number 6 we already have 11. So this is skipped. Then we pull another node with a better answer. So we pull node number 4. But for node number 4 we have for node number 4 the answer is 20. So let's traverse its adjacent nodes. Let's traverse node number 5, and the distance would be 20 plus 6, that is 26. But we already have a better answer than 26, that is 20. So moving from 1 to 3, then from 3 to 6, then eventually from 6 to 5, this path 1, 3, 6, 5 is better than moving from 1 to 4, then from 4 to 5. Okay, so we don't have to update this neighbor for node number 4. Let's traverse another neighbor, that is this node number 2. It has a distance of so if I move through this node, that is node number 4, it would be 20 plus 15. So it will always be a worse result. So traverse 3, it will give me 20 plus 11, that is 31, worse than the distance that I already have. So in this fashion I don't have to update the distance of any neighbor of node number 4. Then pull out this node, then pull out this node, that is node number 5, and try to update the distance for for its adjacent nodes. So what I am doing here, whenever I am pulling out a node from the priority queue, I am pulling the node which has the shortest distance from the source vertex. I am assuming that this vertex which I am pulling out from the queue has the shortest distance. Okay, and assuming that I am calculating the shortest distance for its neighbors. That process is called relaxation. So if I write it in equations, let's say I'm writing the equation for this thing. So in this fashion I will pick up the nodes from the priority queue one by one according to their distances from the source vertex. Then using those nodes I will be updating the distances of their neighbor nodes, and in this fashion I will finally arrive at the shortest path for each node of the vertex, like I did in this case. So if I write the single source shortest path graph for this given graph, then it would be, let's write it, calculate for node number 2, the shortest path distance would be 7. It would be 7. Then from 1 to 3 it would be 9. Okay, because that's what we have calculated. From 1 to 3 it is 9. Then from 1 to 6 we have distance as 14. Then from 1 to 5 we have distance as 20. Then from 1 to 4 we have distance as 20. Okay, from 1 to 4 we have distance as 20. I'll move from 1 to 3, then from 3 to 4, so it is 20. So this is my single source shortest paths starting from node number 1 till each node of the given graph. Basically that's what I am doing. So here what I did is, though the idea is simple, so pick up this node number 1, calculate the shortest distance till node number 6 through this node number 1. It came out to be 14 because the edge width is 14. Then do the same for node number 3, calculate the distance till node number 6 through node number 3. That would be 9 plus 2, which is 11, and this 11 is better than 14. So perform this relaxation. So that is, I will move through this path rather than this path because it is more optimal. So in this fashion, using these intermediate nodes, I'm going to perform the relaxation over every node of the graph, and that calculates the shortest distance till each node of the graph possible. So I'm simply gonna stretch in this string. Okay, so remember, whenever I'm pulling a node from the priority queue, I'm assuming that I already have the shortest distance for that node calculated in our distance array, assuming that I'm trying to update the distance for the neighbor nodes of that node. Fine. So that's basically the underlying idea for Dijkstra algorithm. Let's see the pseudocode implementation. So let's create a function Dijkstra which takes in the number of nodes, the graph, the source vertex and the destination vertex. Initialize a distance array, declare a distance array of size n plus 1 because the nodes are numbered from 1 to n. Then declare another array, then initialize this array with a very large number because we haven't explored any vertex yet. We haven't calculated the shortest distance for any vertex yet. Then declare a priority queue and then push the source vertex into the priority queue along with its distance from the source. So the source is src, which is given, and its distance from the source would be 0. So put it into the priority queue and initialize the distance for that source vertex to be 0 because I'm starting from that vertex. Then run the while loop till that priority queue is not empty. Pop the top node from the priority queue. All of these pairs, distance node pairs, will be sorted in increasing order according to the distances. Okay, so lesser distance node, the node which is closest to the source node, will be popped out first because we have a source node S and we have a bunch of nodes around it. Then if I want to calculate, let's say, the shortest distance till these nodes which are here, then what I'm going to do is I'm going to pick that node from these neighbor nodes which has the shortest distance because it would be better to calculate the shortest distance through that node only, because that node already has a shortest distance out of all these nodes. That's why I am picking up the node which is nearest to the source vertex, and I will pop that node out of the queue. Then I will check if the distance that I have for this node which I am popped is greater than the distance that we have stored in the distance array. So we have already calculated a better distance for this node. That means we don't have to process this node with this distance. So I will simply continue right from here. Otherwise, this is the shortest distance, and I'm gonna iterate over its neighbors. Okay, so here you can see that I'll iterate over the neighbor nodes of this current node, and for the neighbor nodes I'll calculate the weight of the edge which connects this node with its neighbor node and the neighbor node itself. Okay, then I will check if the distance for the neighbor node is greater than the distance which I calculate through this node, that is this one, that is dist plus weight. If the distance that I already have in the distance array is greater than the distance which I calculate through this node, that is if there is a scope for relaxation, then I will perform this relaxation, that is update the distance for the neighbor node, because it is better to arrive at this neighbor node through this node. Okay, so update the distance for the neighbor node and push this neighbor node into the priority queue along with its distance or updated distance. So whenever we update the distance for any node, I'm going to push that node into the priority queue, because I have already calculated the shortest distance for this node, so it would help me to calculate the shortest distance for its neighbor nodes. So in this fashion it continuously performs relaxations here and updates the distance array. Finally we have our distance array prepared, which contains the shortest distance till each node of the graph, that is this one here, this one, and that I'm going to return right from here. Okay, because I want to find the distance for the destination. So that's all. Let's just discuss the time and space complexity for this solution. Let's discuss the time complexity for this algorithm. And this inner loop is going to run for big O of n plus e times. So this inner loop basically runs for big n plus e times, where n represents the number of nodes and e represents the number of edges. Okay, so then inside this loop we can see that we are performing the relaxation here. So whenever we perform a relaxation, we're going to push a new node into the priority queue along with its distance. So this priority queue will adjust this node according to its right position, or we'll say it's a kind of decrease key operation. Okay, so hence this will take big O of n time complexity, big O of log n time complexity for the decrease key operation, log n time complexity for the decrease key operation. Okay, so this is the overall time complexity for the Dijkstra algorithm, for the decrease key implementation of the Dijkstra algorithm. So I'm using a priority queue here. We can also use set data structure. While since we can store at most n nodes in the priority queue, the space complexity would be big O of n. Okay, so that like how to restore the actual shortest path from any given source vertex till any destination vertex. How can I restore the actual path, namely the set of nodes constituting the shortest path? Also, we'll be discussing about the further optimizations, how we can use indexed priority queue, why Dijkstra algorithm is not possible for negative weight edges, and so on. So that's all for this video. If you like the video, then hit the like button and make sure to subscribe to the YouTube channel. I and stay tuned with me to learn more about Dijkstra algorithm, and we'll be solving a lot of problems on this algorithm to understand it better, to get its core idea and to absorb it completely, so that whenever a new problem of Dijkstra appears, you people will be able to solve that problem. So I hope to see you all in my next video.